Okay, so now that you've entered your data, you've done your algebraic analysis to test your functions that you've developed, you're up to the step where you can use technology to test different kinds of polynomial functions. Now, a polynomial function simply means that you've got some sort of function that's like, an expression that where all of the powers above x are positive whole numbers. That's what it means to be a polynomial. So here I've got y equals mx plus c. The power above x is 1. The power above x here would be 0. We've just left that out because we don't need that information. It just turns into 1. So if I turn this line on, you can see it's a straight line. Now in my assignment, I would talk about how a straight line does not fit the shape of the data because it's a straight line. It doesn't fit the curve. So the r squared value for that one is 0.046. So you can see that's pretty bad. Now, when you're writing about this in your assignment, the expression that you're writing about is y equals this value of m, x plus this value of c. So the full expression is, let's see if I can enter one in somewhere. So this actual expression for y equals mx plus c is, and I can test this, y1, little squiggly line. Now that's underneath the escape key. This value of m, so 0.0978848x1 plus 10.89.2. So, sorry, not 0.2, just 2. So see how they've got the same r squared score? Because this is the function that the computer's generated you. To fit the data, the best gradient that it could recommend to you is this gradient with this intercept. Okay, the constant is always the intercept on the y-axis here. Now, if you're looking at this equation below, this one, we can see that that's a much better fit. It's a lot closer to these values. So the regression score for that is 0.99, so it's really close to 1. So that's a much better fit. As I increase the value of the polynomial, which means I'm increasing the highest power that's in there, it's increasing the r squared value. So it's 0.9975, slightly better than that one. So that's what you're talking about when you're comparing the r squared score. Your residuals are where you're plotting the error. So that's the difference between this line and this coordinate. So the difference between where the function actually was and where the coordinate actually is. So if I press that, now I can see down here the error. So the closer everything is to that line, the better it is. Now, I don't actually know how to get the error to go away once you press that button, so you're kind of stuck with it. But you can see here the errors are all below 1, which is pretty good. If I e-plot that one, you'll see that the error is a little bit more wild. So they're a lot higher here. I've got 5s, I've got -4s. It's huge. So that's how we know that one is no good. This one is much better. Okay, so when you're talking about how you can test the fit of your data, you can talk about r squared scores and you can talk about the residual analysis. So the other thing that you might want to do when you're testing, if these aren't going to give you a good form, then you might want to change to a turning point form to see if that's going to give you a better r squared score. So here, if it's a cubic, then it looks like that. That does not fit our data very well. Let me turn off the other function so we can see that one quite clearly. So okay, so cubic doesn't really fit it. Let's see what happens if we change it to a parabola. Okay, now my r squared score is a lot better. What happens if I make it 4? Okay, my r squared score is a little bit worse because it's getting a little bit more of a flat butt. So that's what happens when you put it to a quartic. What happens if we put it to the power of 5? Okay, now the r squared score is terrible. If we put it to the power of 6. So every time that it's even, it's getting a little bit better. That's something that you might want to talk about in your assignment. Let's see what happens if we put it to the power of 100. Well, that's terrible. Okay, so there is going to be a limit to where this thing is actually good. If you don't hit the required number of 0.998, That's okay. If I got to like this one here, I would talk about how that's very, very close, and with rounding that does actually hit our number, but maybe this thing just doesn't get to be that close. We'd have to use a different function, like maybe a trigonometric function or some other form.